Am I audible?
Yes.
My screen visible?
Yes.
Hello. So here we will be presenting on our final checkpoint for CS773 project. Our project title is Hybrid Cache Architecture for Comprehensive Security. Me, Shomik Dotto, along with my teammates Arnab Bhakta and SM Arif Ali. We are Team Gandiva. Let's start with the problem statement. Modern processors are vulnerable to two major classes of attacks. First one is conflict-based attack. Here, attackers try to create conflicts with victim instructions or data in cache hierarchy to infer victims' instructions or data usage. In contrast, for transient execution attacks, attackers tries to fool victim to execute wrong code blocks with speculative executions. So the problem statement is, how can we create an unified solution to defend against both attacks types, keeping the performance security trade-off in mind? So let's see the prior works in this area. First one is Mirage. It mitigates conflict-based cache attacks with a practical, fully associative design. It came in Usenix 2021. And the Ghost Minion, which mitigates the Spectre attacks, it came in Micro 2021. So combining them could provide a comprehensive security, but it requires a careful integration of both of these approaches. So the goal of our project will be first combining Mirage global evictions approach to mitigate the conflict-based attacks. Then we will try to integrate the Ghost Minion to prevent transient execution attacks. And we will, after the both of this integration, we will try to evaluate the performance overhead of this whole integration. And we will use IPC and MPKI for performance analysis. So now brief recap of checkpoint 1 will be given by Arnab.
Hello everyone. This is the brief recap of checkpoint 1. So the Mirage and Ghost Minion was implemented in different versions of Gem5 and architecture. So original Mirage was implemented in Gem5 version 19, which is not replicable in newer version of OSS. So we have ported it to the latest Gem5 version 24. Similarly, Ghost Minion was implemented in version 20, and we tried to port it to version 24, but it was not compatible. So we have fall back to the original version 20 implementation. There is also architectural mismatch. Mirage was implemented in x86, whereas Ghost Minion was implemented to ARM. And we tried to port Ghost Minion to x86, which was not supported. So instead we ported Mirage to ARM. Also, during running the benchmark, we have noticed that checkpointing is necessary to reproduce proper results with matches with the paper. So finally, in checkpoint, we have implemented Mirage artifacts in Gem5 version 24, Ghost Minion in version 20, and we have evaluated all this implementation using Spec 17 benchmark suite. And this is our simulation configurations, which is mostly same for the ARM and Mirage and Ghost Minion. We have simulated this on a ARM64 single core out of order CPU, and the warm up and simulation instructions both are 500 million. And next, this is our Mirage speed up results plot. As you can see, most of the workloads give performance very similar to the baseline or slightly below. There are some exceptions, and the question is why. So next, we look at the MPKI L1 and MPKI L2 plots. As you can see, there is very insignificant change, mostly same. And similarly for MPKI L2, there is very insignificant differences. And next, we are seeing the L1 means latency, whereas for most of the workloads, latency has decreased. And if we check that for the exception plots that DPSGing, LBM, BWaves, etc. These three shows very significant mislatency drop, and those have the performance increase. And next we see the Mirage trade-off. In Mirage, we simulate fully associative cache by using some extra tags, and there are 100 means that there is no extra tags. And as we increase the L2 tag overhead, we use more tags, the local replacement decreases, and around 125 it is 0. Next, there is ghost minion results. As you can see that most workloads give performance very similar to the baseline or slightly low, and average it is 0.98. Next, we have the L1 MP query, which is mostly insignificant. And similarly for L2, there is very less change. And next, we have the ghost minion trade-off. Hereby, we can see that changing the ghost minion size does not really affect the performance. And next, and now checkpoint 2 will be presented by Arif.
I hope my screen is visible.
Yes.
So this is checkpoint 2 work from here. So on the checkpoint 1, the feedback received is we have to take care of those unexpected results that Arnav talked about. So the action that we took for this is we changed our setup of how we are evaluating the benchmarks. So previously, we are starting the benchmark evaluations from the initial, the first instruction. But found out that in the original artifacts on the paper, they were not doing that. So they were taking some checkpoints, which is like they're skipping over the initialization part of those benchmarks, which is about 10 billion instruction, rough figure. And from that onwards, we are evaluating the benchmark. So we are moving our ROI, like region of interest, to plus 10 billion instruction and thereafter. So we evaluated the benchmarks with this checkpoint and use a larger instruction count for this. So this is the previous result that we saw of where the DPSGing and BWaves and these received speed up, which was not expected. So after this checkpointing technique, this is the result that we got. So we see that for this DPSGing and BWaves plot, we are not, the earlier unexpected results are not reproduced here. So we think that that is the checkpointing technique and the more simulation instruction is the reason for this. So work done in checkpoint 2 is this. So we integrated Mirage and Ghost Minion in Gen 5 version 20. And then we also implemented the checkpointing system to skip the first 10 billion instruction and the simulation after that. So there are some configuration that we had to come to a middle ground for this merging. So the DRAM page management policy using Ghost Minion is open adaptive. It is the open page policy which is default in M5. But in Mirage, it was used, a closed policy was used. But in the combined technique, we use open adaptive policy. Open adaptive policy because the DRAM normally is not used in a closed policy because it hurts performance. And inclusivity for Ghost Minion was exclusive. And for Mirage, it was inclusive because it worked at LLC and was mitigation for the conflict-based attack. So it used the inclusive hierarchy. In the combined technique, we also use the inclusive hierarchy to match Mirage's configuration. But we had to keep the Ghost Minion part of the L1 cache exclusive with respect to the normal non-speculative hierarchy. This is a revised simulation configuration. The main things changed here is the simulation instruction, which is earlier was 500 million. We used 2 billion here. Initially, we tried with 10 billion instructions, but each benchmark was taking very long, about 45 hours. We fell back to 2 billion instruction only. So this is the speed up results of the combined technique. So mostly we are seeing that on the geo mean, there is a 5% slowdown on average. And this correlates to the expected results from the both of the papers. There are some benchmarks like BWaves, GCC, and MCF and Zalang, which are having more slowdown than others. We shall see why it is the case. So this is a L1 MPKI plot. So all of the benchmarks like BWaves, GCC, MCF, Zalang suffers high MPKI at both L1. We'll see the L2 results as well. But Zalang is a bit, Zalang and Exchange 2 is a bit exception here because Zalang curious here, there is not much difference in L1 MPKI, but still the performance is 0.88, which is lower than the baseline. And also Exchange 2 has here the baseline value is shown as 0, but actually in the fourth decimal place there is a value. It is not 0 MPKI. But for the combined technique, the MPKI is very high. So, but the performance is not reflecting that. It is not having any slowdown due to the high MPKI. So for the reason for why this is happening, we shall see. Zalang next, we shall see that Zalang at the L2 level is having almost 3 times more misses. More L2 MPK is 3 times than the baseline. So that is the reason why Zalang is having that slowdown. Now also LBM, since LBM is seeing a slight speed up because the Mirage technique uses a randomized replacement policy, so that cache replacement policy might be helping LBM's access patterns. So this is the L1 miss latency plot. We used absolute numbers here as opposed to the relative numbers before. So the main point to see here is Exchange 2, which is having a very less L1 miss latency in the combined technique. This is the reason why this miss latency is basically compensating this speed up, compensating this MPKI, and which is not, that is why it is not affecting the speed up. So yeah, this was the miss latency graph, and yeah, thank you. Sorry, also GitHub link. Thank you.
So yeah, thank you.